Welcome to my project bazaar. Welcome to clickmyproject.com. We are going to see the product for a fully digital front-end architecture for ECG acquisition system with 0.5 volt supply. Next, we are going to see the abstract for our product. In this product, we are going to implement the ECG acquisition system. Biomedical devices are becoming more popular. This is due to the rapid advancement of integrated circuit fabrication. Such devices are being used as wearable or implantable gadgets as well as monitoring equipment. In all these applications, the biosignal is first preconditioned and converted to digital. A digital signal processor then processes the digital data for monitoring or diagnosis applications. Biomedical signal acquisition systems typically consist of a low noise amplifier, a bandpass filter, an analog sample and hold, and an analog to digital converter. With the advancement of CMOS technology, the supply voltage is being reduced, which decreases the voltage headroom for analog block of an IC. Although the scaling leads to low power consumption and higher performance in digital circuits, many parameters such as signal to noise ratio, dynamic range, gain, and so on, the analog parts of an IC are negatively impacted. Therefore, it is desirable to find new architectures in which more digital blocks are used. In our product, we have used more digital blocks. Next, we are going to see the flow diagram for our product. The flow diagram consists of active electrode, moving average voltage to time converter, control logic, counter, DMX bar, decoder, and ECG circuits. The processing of the biosignal is performed in the time and digital domain. The advantages of digital CMOS technology are utilized. The analog biosignal coming from the electrode is directly connected to the front-end circuit and is converted to time with the voltage to time converter. From this point on in the circuit, the signal information is in the phase of the VTC output signal. The output of the VTC is applied to the time mode processing block, in which the anti-aliasing and offset cancellation are done in time domain. Then a time to digital converter transfers the time mode signal into digital domain, where other processes such as digital filtering, data compression are performed. The proposed architecture has these blocks: the control logic has timer comparator, SR latch, 224 decoder is for the decoder architecture, 328 decoder is for the decoder architecture. The counter consists of JK flip-flops. We can use T flip-flops also. In our product, we have used JK flip-flops. The AC coupling capacitors are removed in our product, and the impact of the electrode offset on circuit is cancelled via a feedback loop. The technique used for the offset cancellation is given. An active electrode is an electrode in which some active elements are used to reduce the power line interference. Finally, we are going to see the output for our product. The design is implemented in the Tanner version 13.0. The ECG block consists of the main design, which is connected all the structures. The proposed structure blocks are all connected in the ECG. This is the main design. All the other designs are the parts of the main design. The ECG design consists of the active electrode, MA-BTC, counter, DMX, DCC, counter, and control logic circuits. These are all interconnected. Let's see the waveform for the ECG. This is the final output for our product. Next, we are going to see the designs for the separate for the each block. 3 to 8 decoder is the part of the 5 to 32 bit decoder block. Next we are going to see the waveform. This is the waveform of the 3 to 8 decoder. Next we are going to see the design for the 5 bit counter. The 5 bit counter consists of the JK flip-flops and the AND and OR gates. Next we are going to see the waveform. This is the waveform of the 5 bit counter. Next we are going to see the active electrode. The active electrode consists of the transistors. Next we are going to see the waveform. This is the waveform. Next design is control logic. The control logic consists of the TC and SR latches. Next we are going to see the waveform. Next the design is DCC circuit. The DCC circuit consists of the positive and negative voltage supplies. Next we are going to see the wave. This is the waveform of the DCC circuit. Next the design is for the DMAX. The DMAX consists of 2 to 4 decoder and 3 to 8 decoder. This is the design of the DMAX and its corresponding waveform. Next block is MAVTC, moving average voltage to time converter. It consists of the positive and the negative sides, which is the voltage supply. Next we are going to see the wave. This is the waveform. Next two designs are the separate designs for the MAVTC. These two designs are implemented in MAVTC. Thank you. These two designs are implemented in